Okay, welcome students. Am I audible to all?
Yes, sir.
Okay, so we have to reinstate. So this is going to be what you all have talked about. So just in quick glimpse, I will rush through the slides. I won't talk in details because Nandini and Yukta and Saiba, they have discussed these things. So just quickly, this is a timeline history, how this your DNA genetic material being discovered. And mainly we focus on the two things. One is the discoverer, Meisher, and second is going to be the one who proved that DNA is your genetic material, that is Hershey and Chase. And the last is James and Watson, Watson and Crick, and Rosalind and Wilkins, yeah, Franklin and Wilkins. So these four, they decipher the structure. So and so how you came? This is the experiment about the Griffith experiment that we called rough and smooth Streptococcus pneumoniae. So smooth is going to be virulent and rough is going to be non-virulent. So virulent can change to the non-virulent. How it is going to happen? What is going to be behind it? So that is the Griffith experiment. He performed this experiment in the mouse. So how one converted to the other, and by this event he found that DNA is one which makes you to change to the virulent to non-virulent and killing of your mouse. So other than that. The every McCarthy and these they also performed experiment and then they extracted their substance, their substrate. So Griffith one, it was to the virus only, to the pathogen. Now they extracted the component like what it is going to be your protein, it is going to be DNA, RNA, fat. So everyone, and finally they found that it is a DNA which is behind the transformation. And this Hershey Chase experiment, he also performed at about the replication way. You can say that's a semi-conservative one. So which one is going to be transferring and how it is transferring, whether it's protein or DNA. So phosphorus is a part of DNA and sulfur is a part of protein. So his experiments also confirm that virus, when it is replicating, uh, it is the DNA which is continually moving population to the population, not the protein. So this is again an important experiment. Uh, so these experiments prove that DNA is your genetic material, and then we'll move to the structure of nucleic acid. This is a very important one. Some of these things Nandini and they covered, but as I mentioned, they do not provide the insight. So here I'll show you the insight one. So history wise, again the similar thing. So this is the one thing. What are their component? So the component wise, you can say the sugar is the component one. Second is the phosphate group. So sugar, two types of sugars are there. Both are the pentose in nature. One is the 2-oxyribose, one is the 2-deoxyribose. Second is the ribose. Ribose is the part of your RNA. Deoxyribose is the part of your DNA. And in your ribose sugars, so when you have to what the deoxy term means, so you can see here this location 2, there's H, and here there's OH. So this oxygen is removed, so that's why we call it the deoxy. Okay, so this is a phosphate group. And the third component is your nitrogenous base. So on this basis of nitrogenous base, the difference is created within the nucleotide. So there are the two types of the nitrogenous base. One is purine, second is a pyrimidine. Further purine is of two types, and adenine and guanine. So purine is a 9-membered ring. So both are the 9-membered ring, guanine and adenine, whereas the pyrimidine are the 6-membered ring. And both contain the nitrogen in them. So that's why we're calling the nitrogenous base. Why we're calling it a base? Because nitrogen have 2 electrons in it, so they can donate electron. So the electron donor are going to be base. So one thing you need to focus it again, what is the donor and acceptor? So you can say this nitrogen is a so this one is going to be hydrogen bond donor because H is there in it. In this nitrogen is going to be acceptor only, where this oxygen is acceptor, this H is donor, this H is also donor. So they can form 2 bonds, it can form 3 bonds. So that's why you know that G and C, when they are pairing, there are going to be 3 hydrogen bond. When they are pairing, there are 2 hydrogen bond. So pairing can happen only in a way when the donor is in front of acceptor. So this O is going to be in front of this H, and this H is going to be in front of this N. So this is acceptor, this is donor, this is acceptor, this is donor. So this is the way how the pairing is going to occur. So and correspondingly for your adenine and guanine, so for thymine and uracil also. One thing, how to remember the structure. So remembering structure is based on this purine, you can say, and the pyrimidine. So you can see that in the 6-member ring 1 and 3, in case of pyrimidine, 1 and 3 there is going to be nitrogen. So by this way you can make the pyrimidine 1 and 9. So it is going to be common for all the type of pyrimidine, whether it is cytosine. You can say this is 1, 2, and this is going to be 3. So numbering is then, if you have, I think with Dr. Jaslin teach you how to heterocycles here to number. So heterocycle here to start from the nitrogen. So 1, 2, 3. So then it is going to be 4, and this is going to be 5. Sorry, 4, 5, and 6. So it is going to be like this. So this is the one. So 1 and 3. So odd numbers are protected. You can simply say that. So you are not going to add anything to the odd one. That's the nitrogen 1, 3, and 5. Now to the even numbers are the 2 and 4. So to this even number, in case of cytosine, you are adding a oxy group, oxygen, and at 4, 1 you have to add amino group. Then if you are doing then called the cytosine. And in case of thymine, both 2 and 4 is going to be oxygen. Both are the oxy. Okay, so this is the structural difference in cytosine and thymine. And one more thing is there, the thymine and uracil, both are the structurally similar, except one variation is there. So this is 2 and this is 4. In both you are having 2 and 4 oxygen, but instead of here with the 5 position, you are having a methyl group, CH3. So that's why thymine we also call that the 5-methyl uracil. Okay, so thymine and uracil, that's why both T and U are pairing with A, because they are structurally similar. So only the one difference is thymine is methyl derivative of uracil. Okay, so this is the one difference. And in case of, if you talk about your purine, in purine also odd numbers are going to be your nitrogen. So like 1, 3, 4, 5, then 6, then 7, 8, 9. So odd locations are going to be your 1 nitrogen, 3 nitrogen, 7 nitrogen, and 9 is a nitrogen. So all odds are nitrogen in it. 4 nitrogens are there. So just you can remember where you have to place your nitrogen. Then coming about your adenine. So in adenine, as I mentioned, the odd number is the nitrogen. So the even number you have to put a thing. So at 4 you can't place because the 4 is a part of ring. 5 you cannot place because 5 is a part, 5 you cannot place thing. 4 at 5 is even odd. So then the number is equal to the 6. So this substitution that you can say, as in case of pyridine also, the 6-membered ring is going to be substituted, not the 5-membered ring. So here also the 6 one, the pyrimidine 1, 6-member at the location number 6. Again, it is going to be even number. So here at the even location, you have to place amine group. That become the adenine. Okay, in case of guanine, again the even number is going to be there. So even number is going to be 6 and 2. So you are going to have both position 2 and 6. At location number 6, you are going to have amino group. So at 6 you have oxygen, and at 2 you have the amine. So this amine you have to replace from the 2, then is going to be your guanine. So this is simply the structure wise. If examiner asks you the structure of these, you have to write. If I ask you the structure of even any nucleotide, you have to describe all these structures in your test book also, in your exam sheet. Then nucleoside. So if start combining as 3 different components we mentioned: sugar, phosphate, and nitrogenous base. If you start combining them, then the game of the nucleoside is game. So nucleoside, if you are combining what? We are combining sugar with your nitrogenous base. So combination of sugar and nitrogen base is going to be your nucleoside. So sugar and your nitrogenous base will give you the nucleoside. Okay, so this is so common sugar is going to remain common there. So in this case, how to name them? So while naming them, naming of each nucleoside is based upon the base itself, because base is changing. So that's why as base change, the name also will change the name. So what are the name of your base is there? Like this is adenine. So we are going to add, this is adenine. If you add sugar, so we are calling it as a adenosine. So you can simply say that to the adenine, you are going to add osine with it. Adding osine makes you the adenosine. And if this sugar is deoxy sugar, like you can see here, sorry. So you can say this sugar is, if this is a oxy sugar, so we will call it as adenosine. If this sugar is going to be deoxy, then you will call it a deoxyadenosine. So the same thing, adenine to the adenosine, guanine to the guanosine. Osine thing you're changing just. And if it's a deoxy sugar, then you'll call it a deoxyguanosine. The ribose term we are not calling it, so just deoxyguanosine. And cytosine we are calling cytidine. Here I have in case of cytosine, because already sine is there in it. So we are not to eliminate the confusion of osine adding cytosinosine, we are not calling it. So we are going to call it cytidine. Okay. In case of, so simply you can say that pyrimidine, if they, sorry, purine to purine nucleoside, we are using term osine. Okay. And where they are pyrimidine, in case of pyrimidine, their nucleoside, we are going to call them dene, cytidine, uridine, thymidine. Okay, so cytosine to the cytidine, if deoxycytidine, thymine, thymidine. So thymidine is there, and so you can also call it as a deoxythymidine and deoxythymidine simply to this also. And as I mentioned you, the thymine and uracil are differing in this 5-methyl group. So you can also call it the 5-methyl uridine. Okay, so this is uracil, this is uridine and deoxyuridine. So these are the name how you are calling them. If you add a sugar to it, then you will become if you add phosphate group with it, then you call it as a nucleotide. So at which location you are going to add it? So the location at we are going to add it. So the number is bit crucial. So at which number you are going to add, which number of your sugar, which number of your base they are joining. So that is joining is going to be 1, 9, 1, 9 in case of your purine, and 1, 1 in case of your pyrimidine. Okay, so 1 of your sugar, 9 of your nitrogenous base in case of purine, 1 of sugar and 1 of pyrimidine in case of your pyrimidine. Okay, so where you're going to add phosphate group? Phosphate group you have to add the 5'. So 5 location that we call it the 5'. So these are the ends that you're referring, 5' and 3' end. So in case of sugar, to distinguish whom you are referring, because both are the groups, these are 1, 2, 3, 9 numbers are there, here also 1, 2, 3, 4, 5 are there, so which you are referring. So to distinguish from the nitrogenous base, we put prime with the sugar. Okay, so this 5' means we are talking about the sugar, fifth carbon of your sugar. 3' means we are talking about the 3rd carbon of sugar. Okay, so that's why we are using term prime, and the first prime means you are going to talk about the carbon number 1 of your sugar. So that's why this priming is there to distinguish. That means we are referring the sugar, we are not referring the nitrogenous base. Okay, so then coming to the one more thing, hydrogen bonds are there, Charkov pairing, A pair with the T and T pair with the C. So this is a structure. This also you need to remember how they are pairing. So as you remember that I mentioned you, this is going to be your 1, 2, 3, 4, 5, 6, and so 1, 2, 3, 4, 5, 6. So 6, 1, 2. So these are the 3 on which they are located. They are going to be pairing, and they are going to be in this location. 6 going to be above, then 1, then 2, and this is going to be of your purine. Okay, so this is 6. So this is going to help you in remembering so how you are going to draw this structure. So at each location you are going to have oxygen, hydrogen, and hydrogen, and in it, in this one, this is going to be 1, this is going to be 2, this is going to be 3, this is going to be the 4. So the side which is going to be in front is going to be 5, 1, 2, 4, 3, 2. So you can say that the 5, 1, 2, and 4, 4, 3, 2. So they are the sides which are going to be in front of each other, and that leads to the formation of hydrogen bond. This is this acceptor, this is donor, this is acceptor, this is going to be donor, this is donor, this is going to be acceptor. Okay, so this is the way how they're going to be arranged. And in case of ANT thing, just you need to again remember the number. Numbering is as this is a 1, this is 2, this is 3, this is 4, this is 5, this is 6. So again the things are going to be there here also. 6, 1, 2. Sorry, so this is not 5, this is 6. Sorry, 6, 1, 2, and here again this is 1, 2, 3, 4, 4, 3, 2. So these are the sides which are going to be in front of each other. So here in this case, there is this is going to be acceptor, this is going to be donor, this is going to be acceptor, this is going to be donor. Okay, so this one it can't form any bond because in front of this there is no donor is there. Okay, so that's the reason they are forming only 2 bonds, where GC is forming 3 hydrogen bonds. They are going to form only 2 hydrogen bonds. So this is a pattern in which you have to arrange your nitrogenous bases while depicting how the hydrogen bond is forming between 2 respective nucleotides and respective nitrogenous bases. Okay, so this is a depiction of hydrogen bond between 2 nitrogenous bases, so A and T and G and C. So if you want to change, if the side is changing, one side is going to be C, other side is going to be G. Just you can shift the orientation. So the orientation is going to be just reverse it 360-degree angle, or sorry, 180-degree angle. You will find the similar arrangement that will give you the pairing. Okay, so nucleotides are the thing, combination of phosphate plus nucleoside. It's going to be nucleotide. How many phosphate group are there? On the basis you name them. Naming nucleotide is nucleoside plus phosphate. Nucleoside, you're naming nucleoside is guanosine. This is guanine, so this nucleoside is going to be guanosine, and phosphate is 1. You'll call it a monophosphate. Guanosine diphosphate, guanosine triphosphate. Cytosine you're calling cytidine. Cytidine monophosphate, diphosphate, triphosphate, or you are calling it as ATP, GTP, CTP, TTP, UTP. ADP, AMP, so that's why the main is AMP means adenosine. So you need to remember, in case of purine you are going to use osine. Pyrimidine already having the sine in their name, so we are not using sine there. We are going to call them cytidine, uridine, thymidine. Okay, so these are the names what we are calling. And if the nucleoside is deoxy, we'll call it the DNTPs. Deoxy, the nucleotide is going to be guanosine trinucleotide. Deoxy adenosine dinucleotide or trinucleotide. Okay, trinucleotide phosphate. Adenosine triphosphate, monophosphate. So that's why you are naming them. Then coming to how these nitrogenous bases are linked, because these are these nucleotides, they are the unit of your DNA, and they are joined with their 5' and 3' ends. When we are referring the 5', 3', it means we are referring the sugar. And at the 5' we mentioned that it is going to be phosphate group, and the 3' end it is going to be OH group in your sugar. So the joining is going to happen between the 5' phosphate and 3' OH, and this joining leads to the formation of a bond, to which we are calling it as a phosphodiester bond. So in case of your DNA, there are a type of linkage. First is a phosphodiester bond. This linkage is going to happen between 2 nucleotides. Okay, so here you can see this is a 1 phosphodiester bond. So phosphate group is there between. So diester is there, one ester and the second ester. So that we're calling the diester. And second type is linking is there between your nitrogenous base and your sugar, that we also calling the name of that linking is N-glycosidic bond. So if anybody asks you what are different types of bonds between your in your DNA, what different types of bonds are there in DNA? So types of bond, one is a phosphodiester bond, that is the linking two nucleotides, and the second is N-glycosidic bond, that is linking nitrogen base with the sugar. So here the name, if you can say that the phosphodiester, the name means phosphate is going to be there, and diester formation is there, and in N-glycosidic, N nitrogen is going to be there, and glycosic means sugar is going to be involved. Nitrogen is linking with the sugar. Okay, so this is the thing. This is a Chaff-Off pairing with H pairing with T. So simply means AT is going to be equal to GC. So that sum of all the GC and AT. T and G is equal to C. So amount of, if you just talk about the total number of purine is equal to total number of pyrimidine. So both, but individually if you take the GC and how many GC are there, how many AT are there, so their ratio may be different. But ratio to A and T is always going to be 1. Ratio of G and C is also going to be 1. But separately their individual component, like if you talk about how many AT are there and how many GC are there, they may be the different. So like simply you can see in, okay, this table is not taking about. So A is equal to D, G is equal to C, and A plus G is equal to C plus T. That's so GC content is given for the species. So this is going to be different. Each species is going to have different GC content. Then the structure of DNA, like all of you, Nandini very well explained it, and she mentioned that two different types of things are there. Adenine is there, how they are link joined, and two are running anti-parallel. One is running from 5' to 3', second 3' to the 5'. So this is the how way, and they are twisted around each other. So they are helical way, and in helical they are forming two grooves. One is a major groove, second is a minor groove. So these grooves are notches how DNA is exposed, because when you're wrapping around it, that wrapping around it leads to the formation of these grooves. And these minor and major grooves, small notch we call the minor groove, big notch we are going to call the major groove. So major groove means going to have greater length, minor groove is going to have smaller length, and these grooves are going to be running alternatively. So minor groove, major groove, and both the groove combine together to lead to one twist and one turn or one cycle. And the length of one twist, one turn simply is going to be 34 angstrom, that you call is the unit length, and the width, the diameter is going to be 20 angstrom. So in one circle and one helix, there are going to be 10 nucleotide, as Nandini already mentioned. The distance between individual nucleotide is going to be 3.4 angstrom. In case of, in terms of nanometer, you can say 3.4 nanometer or 0.34 nanometer for your individual distance. Okay. And one more thing is there about the form of DNA. Most of the DNA that we are talking about is a B form of DNA, and whatever the structure is describing you, this we are describing about the B form of DNA. So there are different form of DNA depending upon what environment it is going to be. And the Watson and Crick model, whatever Watson and Crick structure that we are referring this B form of DNA. Okay, we are not referring the other form of DNA. Okay, and so then these features, what different features are the BDNA? So this, as I already mentioned you, the Watson-Crick structure is of B form of DNA. So major groove, minor groove, everything are going to be there in that form. Right twisting. So this is how much twist is going to be there. B form is a right-handed, so right hand twist is there. So you are going to move in a right direction. So if you start moving from the 5' to the 3', then you are trying to find the right. So screw is a right-handed tool. If you keep on, as your screw are there, whether you are tightening right-handedly or left-handedly. So it is going to be a right-handed twist is there. So from top to from bottom to the top upside. Okay. So and again from the top to bottom, again it is going to be right-handed side. Okay, so this is the right twisting, double helix, anti-parallel, base particular base are perpendicular to each other, perpendicular to the axis. That's the basis. So if you just try, they are perpendicular to them, and uniform diameter throughout it is a 20 angstrom. That is the one thing, major and minor grooves both are there in it, and complementary base pairing is there. So this is the feature of your B form of DNA. But distance is there, but width is there, but how much individual distance is going to be there. This all, there is a B of your Watson-Crick structure is going to be here. That's shown in our image also. So then again, some more feature of the B form of DNA, as I mentioned, it is the one which your Watson-Crick described, and it is the main form of DNA. The mostly what DNA are there, that is the B form of DNA. Okay, so right-handed double helix. It is dominating, biological dominant. Whatever our genome mostly correspond to this form of DNA. Okay, so structurally, why simple question is why A is pairing with C, why G is pairing. So one simple thing, reason behind the pairing is one thing is uniformity in the structure. As previous slide shown you that throughout you are having 20 angstrom distance. So 20 angstrom distance is possible only if your purine pair with the pyrimidine. Not possible when purine is going to pair with the purine or pyrimidine pairing with the pyrimidine. So this is the one thing. And second thing is going to the orientation of hydrogen donor and acceptor. Okay, so they are running in a way, they are arranged in a way that they come close together and form respective hydrogen bonds that are possible only when A is pairing with T and G is pairing with C. In other case, it is not possible. So that's why you are having best possible structure and feasible structure for your DNA. Okay, so then other conformation, as I mentioned, A, Z, and 4-stranded DNA is also there, and this 4-stranded DNA is mainly formed in your telomere, and it also formed at the location of centromere in your X means in your metaphasic chromosome. Okay, so now after if we talk about other conformation, how they are differing from the B form. So they are differing, like if A is there, so both are the right-handed. So A and B, they are the right-handed structure. So they have the right-handed double helix, A and B. So about how type of the helix is there is no difference in them. But difference is there in what? Difference in terms of pitch. So B DNA has a larger pitch. Larger pitch means the diameter that we're talking about. Sorry, this length that we're talking about. And hence a smaller width. So diameter is going to be smaller. Okay, so now our time is going to end for this session. So please turn on your camera for recording your attendance. I'm not calling individual's name. Please turn on your camera and exit, and we'll join back after 5 minutes. Okay.